Right. So yeah, today we will continue 3D representation. So last week we discussed a point cloud representation, so which is just a straightforward way to represent a 3D point in your 3D space. So yeah, there is several different cons. The first one is that point cloud can represent a file structure without huge number of points. So huge number of points. But it requires new architecture and loss function because this is the irregular data and this is the irregular and sparse data, and it does not explicitly represent the surface of the shape. So extracting the mesh for rendering or other application requires post processing. So anyway, so this is but we call this very efficient way. So how can we process this one? So for example, in PointNet, they just independently embed or encode some feature vector from the XYG to the 1 by D vector. So it means that when you have the P kinds of point, output point feature is going to P by D. Then because we want, if you want to say handle point cloud level recognition or perception problem like the point cloud classification, just pull the data, 그렇죠? As a D by 1 vector and using the FC or the MLP to classify this whole point cloud. Or you can generate the point cloud from the input images, but it's going to be really hard to output the point because this is irregular data. So one more thing is that how can you learn? How can you learn just a network? So let's say that let's discuss the loss function for the point cloud data. So because this is irregular data, we need a differential way to compare the point cloud data set, like Hungarian matching loss in DTR, as we discussed in audit detection part. In point cloud estimation, in fact, this is very, very similar to the Hungarian matching loss that we discussed in and DTR. So please check that if you're interested. Anyway, in point cloud learning, we just use the sample loss, which is the sum of the L2 distance to the each point nearest neighbor in the other set, which is defined like this. Let me show examples here. 자, here is the two kinds of point cloud set, right? So, blue one represent the point cloud 1, let's say PC1, and orange one represent the PC2. We want to define similarity or distance between the set of the two point cloud. Let's say, for example, PC2 is the ground truth, PC1 is estimated 1 by your model. Anyway, temporal distance works like that. So first of all, for each blue one, let's say X, find out nearest neighbor, let's say Y in S2, like this. So for each blue one. Then just measure the similarity. Let's say dot product. No, it's not dot product. It's just L2 norm between the two set of the point. Let's say, right, so this is x1, 2, 3, and this is the y1, 2, 3. Just measure the L2 norm between x and y. Similarly, given for the each vector y, find the nearest neighbor x, let's say here, and here. Then just measure the L2 norm. Then sum up these two terms to similarly, then define temporal distance. It means that if these the set of the point are similar or extremely same, then temporal distance is going to be the small or it's going to be 0. So that's the one way to define the loss function between the set of the point. This is temporal distance. And then another representation is the mesh representation. So triangle mesh or just mesh representation. It represents the 3D shape as a set of the triangle, not just the point cloud, set of the point cloud. So it consists of the vertex, vertebral, which is a set of the V point in the 3D point like this. this, and this. The vertex. This is similar to the point cloud, but it has additional faces. A set of this triangle over the vertex like this or this. So these two surfaces called base. So that's why by using this triangle representation or mesh representation, we can represent not only 3D point but also the face or shape of the 3D one. So thanks to this such a property, it has been the standard representation for the computer graphics, even in computer vision, and it explicitly represents the 3D shape, 그죠? By leveraging the faces. And it is adaptive. It can represent the flat surface very efficiently, can allocate more faces to area with a fine detail. So like this. For example, in such a homogeneous area, we can represent flat surface very efficiently by enlarge, enlarge the size of the triangle. But when you want to represent the details like the face of this dolphin, for example, we can allocate more faces or more vertex to represent the fine detail better. So this is a very, very adaptive and flexible representation comparing to the box representation. One more thing is that it can attach data on vertex and interpolate over the whole surface because it has additional faces. So, for example, if you just allocate or attach the data on the RGB color on vertex or texture coordinate or the normal vector, then by interpolating over the whole surface, you can just represent the even, for example, RGB color on 3D domain or the texture coordinate or normal vector. So here's an example. So by using such a vertex on images, let's say vertex on color value, and interpolated one, you can just represent the colored meshes, 그렇죠? Color meshes. So it means that even though this is a 3D representation, we can not only represent the geometric information but also the appearance representation. So how can you predict the meshes? The first paper we want to review today is the pixel to mesh generating the 3D mesh model from the single RGB images in DCB 2018. So settings like that. Input of this model is a single RGB image of the object like this. This is just single images, 2D images. Then output is going to be a triangle mesh for the object, like this. So this is the very, very similar to the monocular depth estimation, but comparing to the depth estimation, so it's going to be the full 3D representation. How can I solve this one? So in a high level, it just starts from the ellipsoid meshes like the canonical mesh model. And just deform each vertex like this, or like this to make our ideal meshes, the corresponding meshes given the input images. And then it increases the number of vertex in a corresponding manner. So in first step, it just deformed the 156 vertex in step 1, the first mesh deformation. In second mesh deformation, by using the graph unpooling layer, it's like the unpooling or upsampling layer in just an image 2D feature extraction model like the decoder in UNet or encoder decoder. Then increase the number of meshes to the 6 28. So in this, let's say step 1 and this is step 2. In step 2 model, just like the deform, so 628 vertices. And then by using additional upsampling layer, we just deform the 2,466 meshes, 그죠? To highly detailed representation, 3D representation. So this is the text to mesh model, and each mesh deformation, because this is like how say this is like because 3D representation processing, so this part define like a graph convolution network. So yeah. 다시 해봅시다. 여기가 graph convolution network, and this one, it's going to be like the 2D feature representation. 2D feature represented from the input images, so it's going to be the feature injection to let's say apply to graph convolution network. Let's say graph convolution network in mesh deformation. So from now, let's talk about the detail. So in this paper, key idea was iterative refinement, and graph convolution network in the mesh deformation module, and Vertex-Aligned features here, and checkpoint to train this whole model. First of all, let's say the first idea behind is iterative mesh refinement from the ellipsoid meshes to the final high detailed mesh model. Start from the initial ellipsoid meshes, network the offset for each vertex repeatedly, from here to here, here to here, here to here. And one more thing is that, so I mean the each mesh deformation, they just use the graph convolution, but yeah, I'd like to keep an eye in this slide. I'd like to high level idea of this graph convolution network. So anyway, so this is just like mesh representation, and let's suppose that you have each feature vector, let's say fi or fj. So let's say this is just one vector like this. So idea of graph convolution is, okay, so given set of the vector, let's say fi, we want to make a new vector, new embedding like fi prime. So how can represent fi prime? So it's going to be like, I'll say fi, the feature vector in the current vertex, and then sum of the nearby feature vector across the among the nearby vertexes like this one, fj, 3j, jj. I mean it's going to be the nj. It's like the aggregation across the nearby vertex. So in other words, vertex vi, let's say vi has a feature fi. So new feature fi prime for the vertex vi depends on the features of the nearby vertexes, let's say ni, and use same weight w0 and w1 to compute the whole output. Then just make a new feature vector fi prime from the fi. Then, and by applying the, let's say, graph convolution here, we just, let's say, update the each feature vector at each vertex, 그렇죠? each vertex를 feature vector를 이제 우리가 fi prime으로 바꾼 다음에, and with additional MOP, estimate the offset 3D space. Then we can just define, I'll say, offset. I mean, how much move, how can we move, where to move. So then by considering the whole vertex, we can finally deform illustrated meshes to the, I'll say, our final goal. So that's the graph convolution. So in other words, each of the three these blocks consisting of the stack of the graph convolution layer operating with the edges on the meshes, which edges on the meshes, or the or just like the vertexes, 그죠? vertex on the meshes. But when you just work along the, I'll say, point cloud domain, there's no way to, I'll say, use the image feature. I mean the feature vector extracting from the image, single images. Let's say here, 그쵸? So we need additional idea to use align the vertex feature vector. Align the vertex feature vector. So it means that, so for each vertex, let's say Fi, vertex feature vector Fi, we want to use additional image feature vector. Let's say, right, so given an input images, maybe we can extract the 2D feature volume by using the 2D CNN like the LastNet or VG. Then we can just make a H by W by C as done in, I'll say, backbone model. Then because we already know the camera photo from 3D space, let's say 3D space to the image plane, let's say camera coordinate to the image coordinate. So as we discussed in the camera system, we just extract the feature vector here. Let's say for this 3D point or 3D vertex, we can directly project to the image space. Then we can extract the 2D feature vector by using the binary interpolation of the 2D feature vector. Then just say, right, so this is the Fi, the corresponding feature map, feature vector. So in other words, use the common information to project onto the image plane from here to here, and use the binary interpolation to sample the CNN feature vector and use during the graph convolution. In fact, it's very, very similar to the ROI alignment. because ROI alignment in say object detection module. From the object detection, it maintains alignment between input image and feature vector. 그래서 so when we just review, so ROI alignment, it looks like this. 그쵸? We first extract the CNN feature vector from the input images and just use binary interpolate the feature vector. 그쵸? For example, the segmentation or insert segmentation, but similar to this one in mesh pixel to mesh model, just use the interpolate feature vector to determine 3D feature vector at each vertex. So that's called Vertex-Aligned feature map. Because this is the recorded video, if you have any question, please let me know or please send me an email. So yeah, it was the pixel to meshes, and the one thing is that how can I train this one? Because the same shape can be represented with the different meshes, 그렇죠? Because it means that there is a unique representation by mesh model. So the question is, how can we define the loss between the projected and grounded meshes? So idea is, let's just use the point cloud loss function or the chamfer loss function. So first of all, let's suppose that this is a predicted mesh model. Here's the vertex and here is the faces. And let's say here is the ground truth vertex is with the faces. Right, so let's define a point cloud based loss function for training the mesh representation. So how can I do that? First of all, convert the meshes to the point cloud, then compute the loss. First of all, mesh to point cloud is very, very simple. How? Right. So because this is just a 3D plane or 3D face, then we can just sample the point not only on the vertex but also on the plane. Then it's going to be like point cloud without any surface information. Then we can just apply point cloud loss function like the chamfer loss that we discussed in previous slides. So like this. So, given a ground truth, sample point from the surface of the ground truth meshes, which is going to be the offline process. 그렇죠? We can just make the point cloud representation from the ground truth data. Then just measure the chamfer distance between the predicted vertex as a point cloud and ground truth samples like this. That's a very, very simple or brute force or straightforward way to generate the loss signal between mesh model. Problem is, it doesn't take interior of the predicted faces into account. I mean, the beauty of the mesh model is that it has some face representation or shell representation, but this idea does not use any such surface information. Idea is just sample from the surface of predicted meshes as well during the online procedure. I mean, during the training, just actively sample the point given or predicted mesh model. Then just generate the chamfer distance. So maybe it will be better solution to consider not only vertex but also considering the surface. Problem is you need to sample the online, during the iteration, so must be efficient. And it needs to back provide through the sampling, so maybe it's going to be unstable because it depends on sampled point. So because it has some stochasticity during the training, but maybe this is very, very straightforward way. Anyway, so it was a pixel to mesh model. To sum up, key idea of this model consisting of the iterative refinement, graph convolution, vertex-aligned feature vector extracting from the input images and chamfer loss function, 그렇죠? To train a mesh model. Right, so it was the pixel to mesh model. One more mesh representation or mesh encoder was like the measure channel. So this is like extension of the masker channel, which was aiming to extract the 2D shape or the 2D mask from the 2D images, 그쵸? In generalized Artisan framework. In measure channel paper, given a 2D images, they want to generate triangle mesh for each object. It's not a single mask anymore. It's going to be the meshes, triangle meshes. So in a high level, you can just add one more branch to output triangle meshes, 그렇죠? For each object. That's the measure channel. So in other words, measure channel task is given a single RGB images in masker channel in the generalized Artisan framework. 볼까요? generalized Artisan framework. It just output set of detected boxes, right? And for each box, we just generate or estimate boundary mask location, category level, even insert segmentation map in masker channel. And in measure channel paper, however, it add one more branch like the 3D triangle mesh representation or estimation, similar to this pixel to mesh model. So anyway, so this is the mesh or CNN. One more thing is that mesh or CNN is kind of hybrid 3D shell representation. So first of all, in pixel to RCN, pixel to mesh, for example, it has mesh information module which gives a good result, but topology vertex faces genus connected component fixed in the initial meshes. So this is just like a mesh processing, but in mesh RCN, however, use the 복사 implementation to create initial meshes, then deform these are meshes to the this voxel to the mesh model, let's say mesh model, by using similar mesh deformation in pixel to meshes. So anyway, this is the mesh RCN pipeline. Given an input image, for example, 2D input images, estimate or the segment to the object, 그렇죠? By, for example, by using the mouse cursor CNN, and generate the 3D object voxel, like pixel to voxel model, then transform this voxel model to the 3D object meshes by using some graph convolution neural network. So I don't like to skip the high level or the detailed side of the mesh or CNN, but this is just a result on the ShapeNet data set. So this is input images. This is the pixel meshes, pixel to mesh plus just the version 2, and this is also mesh or CNN output. So it preserves the structure deformation precisely, and this is the another result on the Pix3 data set. So this is input images, and this is the extracted boxes, and this is the estimated 3D model, mesh model, task to 3D meshes, chair to 3D mesh, or table to 3D meshes. So results are very well. So because this is a 3D, output, so when you just drop by project website for this paper, you can just see the 3D, visualization of this model. So I suggest you to visit it here. Another thesis on result, and this is the box and mass prediction by the Musker CNN, for example, and this is the multiple mesh prediction output. So which predict the many objects per scene by using the mesh CNN. This is another result. Box output and mass prediction, and this is a mesh prediction. So one thing is that because this is object to 3D representation, it can predict the occurrent part of the object as well, like this. Even though here is some kind of filler, but in estimate 3D model, it just ignore this part. Why? Because it has some, during the training, it just learned some kind of prior knowledge from the image to 3D model. Anyway, this is another example. So, like this. If segment of failure, let's say here, so if there is some failure segmentation, it's going to be propagated to mesh model as well. So it means that segmented well, it's very, very important to precisely reconstruct 3D information. So as we discussed in the lecture, we have a very, very good segmentation model like the SEM, segmented model, maybe, which means by using the SEM model, we can highly improve the 3D reconstruction performance as well. So that's the mesh representation. The final 3D representation is like the imprecise surface or imprecise representation, which is it's going to be the nerve model, neural radiance field. Alright, so before the nerve or neural radiance field, let me just briefly review the imprecise function for the 3D representation. So I just like that. Alright, so this is the examples of the implicit function visualized in the 2D images. And right, so when you just considering the object shape, so for example, explicit shape is like this here. In implicit function, run a function to classify arbitrary 3D point at the inside here and outside the shape. Then just represent each, this inside and outside the shape information as a 1D value, let's say scalar value from 0 to 1, given each point, let's say R3, let's say for example R3, let's say point, let's say P, let's say pixel P, point P, which means like X, P, Y, P, Z, P. So we have the sum function O, or sum representation O, which represent inside or outside of shape. So for example, when we define the inside object as 0, this point, let's say O of this point, let's say very close to 0, while O, let's say Q, O of Q is going to be 1 in this case. Anyway, in implicit function, we just run some kind of mapping function or mapping function from this P or R3 to the 0 to 1 or scalar value. The question is how to train this mapping function. So the surface of 3D object is the level set, for example, some X, let's say here, which is equal to 1 over 2. Let's say the level set of the level set such that X equal to 1 over 2. It's going to be the, surface point. Surface point. So, beauty of this implicit function is we don't need to memorize whole the point information, but we can just know, we need to know mapping relationship only between 3D point to 0 to 1, 그렇죠? By using the, for example, neural network. Then, if we have only neural network, for example, we can represent any kind of this 3D field sparsely, not only sparsely, but also very, very densely. That's why this is called implicit representation rather than explicit representation. In point cloud or mesh representation, for example. So this is the implicit function. So sine distance function, and let's say SDF gives the another technique, gives the Euclidean distance to the surface of the shape. Or for example, sine gives the inside. Let's say inside is going to be the plus, outside is going to be negative. But the main idea, main idea is exactly similar to the implicit function. So in other words, SDF, it's another kind of function, implicit function. And null, today's topic is another, implicit representation, but more popular representation comparing to the previous implicit function like SDF. So from now on, let's talk about the NERF, the neural network field for the view synthesis. I just like that. Input. So first of all, NERF paper starting from the novel view synthesis. The task is like that. Given input images, let's say many images of the same scene with a known camera parameter like this. So this is the multi-view images taken under the same scene. Taken under different camera viewpoint for the same scene. So the novel view synthesis, and the output of, the goal of the NERF or novel synthesis is like generate or the render the images showing the scene or same scene from the noble view. So this is just a noble view. I mean a noble camera pose. We do not have any ground truth data, but this is just a render data. So question is how to render such a noble view by using the algorithm. That's the strength of the NERV, which is called the referring the scene as a neural legends field for diffuse insisting in the ESTB 2020, which this paper is called the NERV paper. So, first of all, to solve this problem, explicit representation like the meshy or the point cloud is very, very limited. Why? Because it is limited to increase the detail. But to render such a high query detail, maybe we require some implicit representation. That's the starting from the NERV. 자, to discuss the NERV representation, let's stepping back. Pinhole camera model. 자, give the camera, for example. So, your sensor, for example, CCD sensors record the light at the end of at the end of the camera hardware. Then when it's just pinhole camera setting, most of your camera pinhole camera, and let right in. So from this light to this light, your camera sensor record this light information. So this is also principle of the pinhole camera model. And one more thing is that this is focal length, for example, which is defined by the camera setting. And let's suppose that here is the light source that emit the light, as a sun, 그렇죠? And let's suppose that here is the object in the world, 3D world, reflect the light. Then this light can be reflected to here. Then your camera sensor can recognize such a output. I mean such a red color appearance. 그렇죠? Appearance. Then, but here is some setting. First of all, maybe there are some opaque object which block the light. It means that even though sun's reflected to here, your camera does not capture any 3D any appearance information due to this one. Or maybe there are some kinds of the transparent object which attenuate light sources, light information. Then in this case, your light can alive here, but it's going to be attenuated. 그렇죠? So in volume rendering, which is a key idea or key module in your NERV model, abstract away the light source object for each point in the space. Let's say each point in the space, we need to know, the model, such a situation, we need to model. First of all, how much light does it emit at each point? Let's say point. And how opaque is it? Let's say sigma from 0 to 1. This is transparent, but this is opaque object. So question is, how much? How opaque is it? So that's the volume rendering one to consider. So for example, point on a cord, emit red light in hemisphere like this one, and it has completely opaque value like let's say sigma is equal to 1. However, this point in empty space, for example, it emits no light, so it's going to be black, and it's completely transparent. So opaque like the sigma is going to be 0. Similar to this one, if we can model such information like the emission or the opaque say degree, then we can just model say this real 3D symbol precisely. That's the idea of the volumetry. So from now on, let's specifically talk about how to model such a two properties and how can we use some kind of mathematical tool or the neural network to render the images, 그쵸? To, I'll say, resemble such a real-world scenario. So yeah, that's a volume rendering. I think that's enough. So if you have any question, because this is a recorded video, if you have any question, please send me an email. So the next lecture, we will finish the neural network field and let's move to the next topic. Maybe it's going to the final topic, generative model, right? So yeah, thank you very much. I think that's enough and see you next maybe week. See you next week. Thank you.